The nature of logarithms is unique in mathematics because it pretty much is a set of rules about rearranging parts of an equation, and logarithms allow us to rearrange parts around. Now we are going to introduce you a few more ideas. The first is called the change of base. Now, if we were to look at a calculator, for example, Desmos, we're going to see the log button here, but that log button is only base 10. And then there's this other button which we're going to talk about today. So there isn't any opportunity with Desmos, for example, to do, let's say, if I needed to do log base 2 of 5. So because of that, we introduced you the idea of change of base. So let's say I do have, for example, log base 2, 5. And I know that my calculator can't find base 2. Well, I can rewrite this. I go ahead and take this 5 and this 2, and I can change it to any other base that I want. So if I wanted to do base 3, for example, I could change it to base 3. But that's pretty useless for us because we're doing a change of base because our calculator can't do base 3 or base 2. But it could do base 10. So for example, I could do just put a 10 here. Or because our calculator doesn't even have a base, right? It's understood to be base 10. I could simply rewrite it as this. So what I'm proposing to you is if I wanted to find what log base 2, 5 is, I could trick the calculator into giving me the answer by doing log 5 over log 2. So looking at A, we could rewrite this as log 7 over log 2. Now again, we could write this as any type of another base. We're choosing base 10 because our calculator can do base 10. And if I'm not putting base 10 there, it's because it's understood that it's a common logarithm. And if you're confused on what's going on, go back and watch the previous video where we talked about common logarithms. So I'm proposing to you that if I put this in a calculator, I would get this answer. Let's go ahead and do that. So put in the calculator, I get this decimal value right here. Part B, well, these are the problems that I told you that we would tell you more when you're older, and here we are. So back in the day when we did exponentials, we had to get them to be the same base. Well, how do I get 2 to become a 7 or 7 to become a 2? I don't. So we're showing you finally, it's been 3 videos now, but we're finally showing you how to solve these problems. I can't make these the same bases. If I could, I would. That's the easier way to do this. Well, we could apply ELB, right? The exponent is the logarithm of the base, and then the argument is there. However, I can't put this in the calculator, so I could conveniently use the change of base formula to go ahead and write that out, and then I could put this in the calculator. And we get this type of answer. Now note that it wasn't really that much harder of a problem as long as you understood the concepts. What we do note is that logarithms allow us to solve problems that we couldn't solve previously, right? Exponentials that we couldn't solve by getting the same base. Well, logarithms allow us to solve those problems. You could do the same thing with part C. You should try it out, but at some point you're going to probably get log base 5 over log base 3. We can go ahead and do this as well with the change of base. Log base 10, right, common log, over log, same base, 10, common log of 5. Remember, you know, we could, if we wanted to change this to base 7, we could. Or 17 if you want, we could. The idea of change of base is I can change this to any other base that I want. Currently, we want to use the calculator to our advantage, so we would go ahead and use something that's on a calculator like the common log. Now, just to give it a sneak peek, right, if I write this one, log base 2 over log base 3, a while back when we talked about exponentials, I may or may not have brought up something called E. E is a number that's kind of like pi. It's like it. E is a number like 2.71 dot 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 dot. And it happens to be a number that's very important and useful in mathematics and science, in growth, in decay, in a lot of applications. In particular, if you're looking at money and funds and investments, E ends up being a very important number. So because of that, because E is a number, we could do pi, for example. We could do log base pi if we wanted to be cool like that. But there aren't any real practical applications of doing log base pi. However, there are multiple applications of doing log base E. Remember, E is a number. Okay. So just to give you a sneak preview, we could do common log. We could also do base E, and I'll tell you more about that very soon. Okay, so here are some laws, some properties of logarithms and how they deal with each other. So I need you to notice a couple of things here. First, notice that on the left side, I have a part of an equation. On the right side, I have another part of an equation. You'll notice that they all have the same basis. So we're not changing any basis anymore. Okay? If you look at all of these, they have the same basis. So we're not changing basis right now. Next, notice that on the left side, I have this, and on the right side, I have this monstrosity. So notice, for example, that I have one logarithm here, but then I have multiple logarithms over here. Notice that this has an interesting argument. There's multiple things in the left side's argument. Notice over here that each logarithm has a single item for an argument. The big takeaway here is that if you multiply, you end up adding. And if you add, you multiply. So it's kind of like what you've learned in the past with other math topics, but for logarithms, it's a bit more defined, right? So I don't want to say that the opposite of multiplication is addition. Usually when you say opposite, we're talking about inverse operations. For logarithms, these are properties that follow as a result of using a logarithm. Okay, moving on to the next one. Here in this argument, you'll notice that there's a division. And notice that usually with these arguments that are more complex, they're going to be surrounded by parentheses so that you're aware that this is one argument for this logarithm. So here they're dividing, right? A quotient is division. And then division ends up giving me subtraction. Notice how the numerator goes to the left and then the denominator goes to the right. Okay. And it is not just two. You're going to see soon that we can do multiple ones. Okay. We'll make sure to break it down for you. But we're telling you right now, division is subtraction, and subtraction is division for logarithms. And then there's a special feller. So what if your argument has a power, p? Well, you take that p and you drop it in front. And it's just p times the logarithm. So it's that power, right, or that exponent times the logarithm. And what if you have a number in front of the logarithm? Well, you put it back up as a power if you want. Okay? That may not have made any sense. So let's show you some examples. A, well, we don't have any divisions. We don't have any multiplications. We do have a power. And so this power can go ahead and jump right in front. And that's it. We're done with that one. That's it. You may need to replay that. That may have been too fast. Okay, and that's because we had a power. So the power jumped in front of the logarithm, and that's it. Okay, part B. This time we have a multiplication. And multiplication means addition. Now to help us out, how many things do I have in this argument? There's a 5, and there's an x. There's 2 things. So I'm going to have 2 logarithms. And it's multiplying, so it's going to be addition. So I'm going to have log base 3, 5, plus log base 3, x. Now, the instructions, which I didn't reach for you, were to expand, and that's what we're doing. So what I'm proposing to you is that this on the left side, if I expand it, is going to give me that. Notice I have the same base. And I had 2 terms in argument, so I have two logarithmic terms. And I split that argument into both of them. For this one, we have a division. Division is subtraction. So I'm going to do the 2. And then minus log base 7 of the denominator. D and E are very important because you need to compare those. Notice that this entire thing is in parentheses. This squared belongs only to the x. It does not belong to the 3. This is very important. You might want to pause, put a star next to this, write something in your left column about this, write some information about this. Very, very important. Because in E, this 2 belongs to, is touching, this exponent is touching the parentheses. So this 2 applies to everything in here. But in part D, the 2 is only touching the x, so it only applies to the x. So let me kind of do D a couple of let me break it down a few ways. First, it's multiplying. Multiplication is addition. But we then notice that this little 2 up here with this x squared is going to go ahead and fall in front of this logarithm. It belongs to this logarithm. So we have log 5, 3 plus log 5x, and this 2 is going to be in front of this log. So this is the expanded form of part D. Now for part E, this 2 belongs to everybody. So you can do this a couple of ways, but I'm going to suggest that let's put the 2 in front first. So we get, I'm going to do it over here, 2 log 5 3x. And then there's the times in here, so I have 2 terms in here, so I'm going to create 2 logarithms now. 2 log 5 3 plus 2 log 5x. I need you to note that with part D, only this second logarithm had the 2 in front. In part E, both of them have that. Now, if that expression doesn't make sense, let me try a different way. Some of you might be more comfortable with me taking care of this square first, right? So I could do log 5 3 squared x squared. Okay, so I gave everybody that too. And don't make the 3 squared into a 9. I mean, just leave the powers. Like we're pretty much asking you and begging you not to do that much math right now. You're just rearranging things. So I'm gonna give everybody this too, right? I didn't do that in the previous problem because the 2 wasn't on the outside of the parentheses. Okay, this is an algebra 1 idea. This is a pre-algebra idea. On part E, the 2 is on the outside of the parentheses, so I'm going to go ahead and put them in both. And so that's what I did right here. Now I have 2 terms, and they're multiplying, so I could rewrite this as log 5 3 squared plus, because multiplication is addition, log 5x squared. And then I could drop this 2 in front, and I can drop this 2 in front. And we get the same result as before. Okay. Nevertheless, it is different than your answer to part D. So please, notice that. Part F, I have confidence in you that you can get part F without me. And this is what you're going to get when you expand the entire logarithm out. Again, note that you begin with 1 logarithm. All these problems for problem 2 began with 1 logarithm, and then we end up with a massive amount of logarithms after that because we're expanding. These problems are asking us to expand. Okay. Part G. Part G doesn't have a base, does it? Oh, if you don't write the base, it's a base 10. Do you have to write the base 10? No, you don't. Okay. We can go ahead and just take care of this guy. The 3 belongs to the x only. So I have if it helps, put a dot in between. That means I have log 6 plus log x to the 3rd power. And then I know there's 3 in front on top of this x, so I can drop it in front. And I'm done with that problem. So I propose to you that log 6 plus 3 log x is the same as this logarithm right here. Great. Not a lot of math. We just done a lot of organizing, right? Take some time to use some words. Comment on the difference between problem 2, part D, and part E. Because I know I explained it a lot, but you didn't write many words. I need you to write down words. I need that to be clear. That's going to be a test question.